The first thing that should come to your mind when you talk about rolling is a combination of two types of motion. Let's say this is a circular object. It can be a disc, it can be a sphere, alright? It has to be round shaped. So you can clearly see that there is a combination of two types of motion. The three different cases here is forward slipping, backward slipping and pure rolling. How does a bicycle work? So, after learning rolling, it is going to be a completely new perspective towards. Hello students, welcome in today's class. What are we learning today? Today we are going to talk about rolling motion. Now rolling motion is something that you keep observing around you, but it's a very important topic. Today we are going to do a detailed physics of rolling motion and I really hope you're going to enjoy this class. Alright, so I think we can start. The first thing that should come to your mind when you talk about rolling is a combination of two types of motion. What are these two types of motion? So first is translatory motion and second is rotatory motion. So just to begin with, first you keep in mind when you talk about rolling, there are two motion coexisting. What are these two motion? The first is basically translatory motion, but translatory motion of center of mass. So look at this now. Let's say this is a circular object. It can be a disc, it can be a sphere, alright. It has to be round shaped, alright. It can be a cylinder. Now very quickly, the first thing that should come to your mind is that it has a translatory motion. The center of mass is moving forward. It has a translatory motion. At the same time, there is a rotatory motion of the object around this center of mass. So again, two things. It is a combination of two types of motion, translatory and rotatory. Translatory motion of the center of mass with some velocity, let's say v, and the rotatory motion of the object around this center of mass. So keep that in mind before we actually start with this topic. Alright, so put down the heading rolling motion, draw this simple diagram to understand that what rolling is. It is a translatory motion. You can elaborate. Translatory motion of center of mass, alright, that is the first thing, and rotatory motion of the body about center of mass, alright. So obviously I am assuming that you already know the basics of rotational motion. Only then you are eligible to understand rolling motion. So you know the basics of rotational motion, you know what is moment of inertia, you know what is center of mass. So all these basic things you should already know. Only then this class will make sense to you. So put down the heading, I'll wait here and then we move forward. Alright, so I hope you've written this. You can pause the video and write this. Next, so let's now do a little more detailed analysis of this. So you can clearly see that there is a combination of two types of motion, velocity and angular velocity, and because of that all the objects on the all the points on the object will have these two motions combined. Let's see how. So for very simplicity, I've considered 4 points here first. This is A, B, C and D. A is the topmost point. Now let's first consider the translatory motion. Since this object is translating forward, all the 4 points are getting that velocity forward because we are learning rigid body dynamics. So all of these points will acquire that velocity. Now let's look at the rotatory motion. So as you know, because of the angular velocity, all these points will have a linear velocity which is simply governed by v is equals to r omega. Alright, so this is r omega. Now look at the sense. This will acquire this velocity forward, this point will acquire r omega downwards, this will acquire r omega backwards and this will acquire r omega upwards. So if you want to talk about the net velocity, so for A it is going to be v plus r omega. So we are looking at different points of the same object. They are all moving with different velocities. Alright. Now what about this one? So you would say the net velocity would be somewhere here, given by v square. Okay, so I'm talking about b, v square plus r omega square. Similarly for this, v is forward and r omega is backward. So this is going to be c net velocity is going to be v minus r omega. Yes, v minus r omega, or you can also write r omega minus v. So who will decide that, whether v is more or r omega is more? So if v is more, then the net velocity of c is forward. If r omega is more, then the net velocity of c is backward. For d, we will say it is the same as b, just that it's going to be in this direction. And for a, as we had written, we can write it here as well, that for a, the net velocity is going to be v plus r omega. All right. So keep this in mind, that when we are talking about rolling of the object, it is a combination of translatory motion and the rotatory motion, and that is how we are talking about the net velocities of different points, that is a, b, c and d specifically. If you want to talk about any other point, you can do the vector addition of v and r omega. It's not a big deal. But what do you think, out of a, b, c, d, which is the most crucial point on the object? Think about it. Have you thought of it? The answer should be C. The answer should be C. C is a very special point. Now understand why. Because C is the point that is going to interact with the surface. So rolling, depends on this particular point. Now this is not a static point. Every time C will change. So in a way, like right now, this particular point, let's say I mark it like this. Let's say there is a red spot here. So this point is representing C, but very next moment, some other point will become C. So C is not a fixed point on the object. Whoever is at the bottommost point is called as C. All right. So this is the point of contact. Now, as I said, this can be V minus R omega or R omega minus V, or can we have a special case, or it can be 0 also. Think about it. What if V and R omega both are equal? Then the net velocity of C would be 0. So we will talk about these cases one by one, but the first thing that again you should understand is this and all the other things. So for example, kinetic energy. For example, kinetic energy now will be written as kinetic energy due to translation plus kinetic energy due to rotation. Now think about it. Whenever an object is rotating, does it have a kinetic energy? Answer is yes. That is called the rotatory kinetic energy. What is the formula for translatory kinetic energy? You would say half m v square. What is the formula for rotatory kinetic energy? The answer is going to be half I omega square, and this is representing the total kinetic energy. This is representing the total kinetic energy. So sometimes you might just get a question that if an object is rolling, what is the ratio of rotational to the total kinetic energy or translational to the total kinetic energy? So you should keep in mind that total kinetic energy is kinetic energy due to translation, this, and kinetic energy due to rotation. All right, half mv square plus half I omega square. So now you have a good amount of analysis that what rolling is. So if now you see any object rolling, like a roller, like a wheel, then you can understand that it's a combination of translatory motion and rotatory motion. Very common. You can see around yourself many times rolling motion, and easily you can correlate with these two motions, that is translatory plus rotatory. All right. So you can copy this down, the basics, and pause the video and copy this down, then we move forward. All right. Next we talk about the different cases that I have for you. So the three different cases, as I was discussing about C, what are the three different cases? So the three different cases here is forward slipping, backward slipping, and pure rolling. As the name implies, what is going to happen, let's discuss. So this was point C. All right, this was point C. The first case is the case of forward slipping. When does this happen? So the answer is when you give V greater than R omega. So when you start off the motion of the circular object, you give V that is more than what is the value of R omega. So think about what is about C. Where is the net velocity of C? So you would say V is greater than R omega. So net velocity is forward, in which the object is going. That is why it is called as forward slipping. So this object is slipping forward, isn't it? This object is slipping forward. What about friction now? If this point is slipping forward, you would say friction will act backwards. Friction will act backwards, right, in the direction of R omega, because V is dominating here and R omega is lesser. So friction is going to act backwards. Now think about what this friction will do. So this friction will act backwards. I will write it here. This friction will act backwards. It will give an acceleration to the object backwards as well, isn't it? Since friction is acting backwards, the acceleration is also backwards. Now this backward acceleration will ultimately cause deceleration, in fact, because you know velocity is forward and friction is acting backward, so it will cause deceleration. So it will cause the velocity to reduce. So whatever was the value of V, it is trying to reduce that V. What about the torque of friction? So you would say friction is acting like this, and if you talk about, you know, the torque about its center, then it's clockwise. So torque of friction is clockwise. That is in the same sense as omega. That is in the same sense as omega. So what will it do? It will cause an angular acceleration also clockwise, isn't it? So clockwise alpha, clockwise torque will now increase the angular velocity. Now it will increase the angular velocity. Let's look at it again. V was forward, friction was backward, acceleration was backward, and therefore V is reducing. V is reducing. On the contrary, the torque of friction is clockwise, which is increasing omega. Think about this now. Friction is acting like, you know, it's trying to maintain the balance. If V is more and R omega is less, friction is trying to decrease V, but at the same time increase R omega, so that at one point both match. So after a point, both will match. That is, V will become equal to R omega. That is the case of pure rolling. That is the case of pure rolling, when V becomes equal to R omega. So if V is equals to R omega, think about it, the net velocity of C would be 0. So this point will always be at instantaneous rest. This point will always be at instantaneous rest. So what is the need of the friction? There is no need of friction, and we can say that friction is 0 or it is static. Whatever it is, the work done by friction will be 0. So in a way, there will be no energy loss. Friction will cause no energy loss. That is why having rollers is always a good choice. Imagine if the rollers are there or ball bearings are there, you can easily reduce the effect of friction and you can easily make that object move to large distances without much effort. In fact, if pure rolling happens, what is called pure rolling, then almost there is no energy loss due to friction, and it is only the air resistance that stops the object. So that's very fascinating, that friction, in spite of the surface being rough, friction is not playing any active role here. But that's only when it is the case of pure rolling. Okay. Now think about backward slipping. When does this happen? When V is less than R omega. When V is less than R omega. Let's quickly look at it. So R omega is more than V. So which direction C is going to move now? So you would say C will move towards the left. C will have a net velocity towards the left. Why? Because R omega is greater than V. So somehow you've managed something, because of that R omega is greater than V. So C is slipping backward even though the object is going forward, but point C is going backward, and friction will be judged by this particular point. So friction will act in the forward direction. Friction will act in the forward direction. Surprising. Object is going forward, but friction is also acting forward, because friction has nothing to do with this. Friction is only bothered about point C. That is why I was saying point C is a very important point. Alright. So friction is acting forward this time. So acceleration is also forward and velocity of the object will increase. Similarly, the torque of friction is going to be this time round, it is going to be anti-clockwise in this situation. Alright, and if it's anti-clockwise, alpha is also going to be anti-clockwise. And since omega is clockwise and alpha is anti-clockwise, so what will happen to omega? It will decrease. It will decrease. So think about it now, that friction is trying to, this condition or this condition, friction is trying to bring it to this condition. So friction is always in the favor of pure rolling. So if you start with forward slipping or you start with backward slipping, in both the cases, friction will convert this to pure rolling. And if it's a good amount of friction, then this stage will convert to pure rolling even earlier. Okay. So keep in mind, again I am repeating, keep in mind that there are three possible cases of rolling: forward slipping, backward slipping and pure rolling. Forward slipping, backward slipping and pure rolling. If the surface is rough, even forward slipping will become pure rolling, or backward slipping will also become pure rolling. But once pure rolling starts, then friction will become zero or static, because point C will have net zero velocity. Okay, so we can write this down. If it's forward slipping or backward slipping, if it is a case of forward slipping or backward slipping, friction will try to convert that into pure rolling, Okay, so are you understanding? In this case, point C is slipping forward, that is in the direction of motion of the object. In this, the point C is slipping opposite to the direction of motion, and in this, point C is not slipping, it is at instantaneous rest. So these are the three cases. You copy this down, then we move forward. All right, now let's take an example of bicycle here. So there is this bicycle, you've all seen a bicycle, you ride a bicycle for sure. So now how does a bicycle work? So after learning rolling, it is going to be a completely new perspective towards riding a bicycle. So what you do, how do you ride a bicycle? How does it move forward? So you would say, we just pedal the bicycle. How does it move then? So when we pedal the bicycle, let's put up a line here just to show it as a surface. So let's say this is the bicycle, and what I'm doing is, let's say this is the surface. Now imagine you pedal and therefore you rotate the back wheel. You start rotating the back wheel. Okay, so you've suddenly provided it with an omega, with some angular velocity omega. So this point C of this back wheel will start slipping backwards. It will start slipping backwards because there is r omega, but there is no v. So this will have an r omega that will make it slip backwards. So is it the case of backward slipping? Of course it is. Now as it is slipping backwards, suddenly a friction will be induced and it will start acting forward. It will start acting forward. All right. So this is backward slipping. So friction is acting forward. So are you moving the cycle? The answer is no. You are just rotating the back wheel. The friction is moving the cycle ahead. Okay. So now since the friction is moving the cycle ahead, or the back wheel ahead, the frame of the cycle is also moving, and since the front wheel is attached to that frame, the front wheel will also start moving forward. So it will suddenly acquire a translational velocity v, but still it is not rotating. There is no angular velocity to the front wheel. So what is this case then? You would say this is a case of forward slipping, because there is v but there is no omega. So this wheel will start slipping forward and friction will not allow that. So it will act in the backward direction. It will act in the backward direction, and when it will act in the backward direction, this wheel will get a torque clockwise. So it will start rotating. It will start rotating. So in a way, can we say that this is forward slipping? Yes. So what good example we can think of than this, where we are seeing both the forward slipping and backward slipping, you know, at the same time. So we are doing what we are doing. We are just rotating the back wheel. As it is rotating, it is acquiring omega, but there is no v. So this point starts slipping backward. Friction acts forward. Since it acts forward, the cycle starts moving, and when the cycle starts moving, the forward wheel, the front wheel starts slipping forward, and friction acts backwards. So can you realize now which direction friction is acting on the back wheel? Answer is forward, and on the front wheel, answer is backward. So this is a very common way of explaining rolling wonderfully, while, you know, contrasting in both forward slipping and backward slipping. So the back wheel is backward slipping and the front wheel is forward slipping. Yes, is it fine? So can we move forward? Are you able to understand? So are we moving? My last question, are we moving the cycle? Answer is no. We are just rotating the back wheel. Who's moving the cycle? The answer is friction. Imagine, what if it would have been a rough, smooth surface? What if it would have been a smooth surface? Sometimes it does happen that your cycle does not move forward that well when it's a smooth surface. That is because you don't get sufficient friction. So if you have sufficient friction, you would be able to move forward very easily. That is why friction is not acting as a villain here. In fact, friction is providing you that forward push. It's only because of friction that you're moving. You must have seen a unicycle as well. This is like bicycle. A unicycle is just this arrangement. When you are sitting on the wheel itself, there you are moving forward because of friction. Alright, so this was my attempt to explain you how rolling is happening in like both the cases are happening at the same time, and I really hope that you were able to learn this. Now let's do a little mathematics of this. Okay, so till now I have done the whole qualitative analysis. Now let's start with the mathematics of it. So I will wait, you can draw this diagram roughly and then we move forward. Alright, one more thing, if you are unable to copy these diagrams, we will definitely share these slides in the description, and you can access those slides from the description and use them later. Alright, so let's do a question. A disc starts rolling on a horizontal rough surface with coefficient of friction mu, okay, with a linear speed v naught. Okay, alright, so let's take a disc first. So let's imagine a disc very quickly. So this is a disc. Alright, now what do we have here? We have a velocity v naught and we have an angular velocity omega naught, such that v naught is 3 times of r omega naught. So which term is more, v naught or r omega naught? Answer is v naught. So v naught is 3 times of r omega naught. Therefore I will straight away write that v naught is greater than r omega naught, and it is the case of forward slipping as we have discussed. So identify the type of rolling. So the answer is rolling with forward slipping. Alright, then the time after which the disc will start pure rolling. So let's quickly imagine that this is the surface, and let's draw the free body diagram. So mg will act downwards, n will act upwards, all that you know. I can still show it very quickly. Mg will act downwards and normal contact will act upwards. Since this is moving to the right and slipping to the right, friction will act to the left. So let me quickly show friction here, and since this is slipping, so I can write friction is equals to mu n, and n is equals to mu mg. Alright, so n is equals to mg, so friction is equals to mu mg. Now that is equals to ma. So I'm assuming that you know the basics of mechanics. All right, so A is equals to mu g. A is equals to mu g. So the first thing that you need to keep in mind, that it is accelerating, or let's say decelerating, with mu g. All right, now let's talk about the torque of friction. So you will write the torque is I alpha, of course. Now what is the torque of friction? F times perpendicular distance. Perpendicular distance is going to be r. Since it is a disk, I will use the moment of inertia of a disk, that is mr square by 2. All right, and then there is alpha. So alpha value turns out to be, let me in fact first put the value of friction. So friction is mu mg into r is equals to mr square by 2 into alpha. So alpha turns out to be 2 mu g upon r. So I've done my preparation to solve this numerical. I've calculated the value of A, I've calculated the value of alpha that the friction is providing. Where do I go now? Look at this. Now I will go towards the first equation of motion, that is V is equals to u plus at. Since I have to talk about the time, the only option that I have is to use the equation of motion. So V is equals to, instead of u, we are using V naught plus A. So instead of plus, I am writing minus mu g. I am writing minus mu g. Why so? Because if velocity is forward and it's opposite, so I am taking rightward as positive, so it's minus. All right, t. So this is the governing equation, how velocity is going to decrease with time. Now similarly, omega is equals to omega naught plus alpha t. Now what is omega? What is omega? Or let's say omega naught plus alpha. Alpha is like 2 mu g over r into t. Now this is my governing equation of angular velocity. So I have the velocity function, I have the angular velocity function. When pure rolling will start, can I write V is equals to r omega? Can I just write V is equals to r omega? Of course, yes. So what is the value of V here? So let's put it here. V naught minus mu g into t. All right. And what is the value of omega? So omega naught plus 2 mu g by r into t. So are you looking what I am doing here? I am writing. So as I was telling you that, you know, V is going to decrease and omega is going to increase. I am writing that equation, how that is happening. So if I multiply, what am I getting? V naught minus mu g t is equals to r omega naught plus 2 mu g t. Now I put the value of r omega naught as V naught by 3. From this equation, I put r omega naught as V naught by 3. So this becomes V naught minus V naught by 3 is equals to 3 mu g t. And the value of t turns out to be 2 V naught by 3 and again 3, 9 mu g. 2 V naught by 9 mu g. That is the answer to the second part of the problem. Like first we've already done that, identify the type of rolling. The second part, the time after which the disk will start pure rolling. So this is the answer, 2 V naught by 9 mu g. It's going to be a very less amount of time. So even if you start forward slipping, friction will quickly convert that to pure rolling. Okay, you can see this twice, there's no problem, but I have to, you know, continue with the solution. I cannot wait for you to understand this. So if there is some part you want to understand again, then you first do that before moving on to the next part. All right, so copy this down. What is happening here? How did we, you know, write the governing equations? How did we get the value of A? How did we get the value of alpha? And then use the equation of motion to get the value of time. Copy this down. I will wait in like I will move aside, you copy this down, and then we move forward. All right, now what I'm going to do is I'm going to use the same thing. So now we have the time. So let's find the final linear speed. So V is equals to V naught minus mu g, and time we have just calculated 2 V naught by 9 mu g. What was the time? 2 V naught by 9 mu g. So I've substituted the value, and the value of V turns out to be, so this is going to be 7 by 9 V naught. What is it? 7 by 9 V naught. This is the final linear speed when pure rolling starts. Now, what about omega? So, omega final is just V by R, because now it is already in the state of pure rolling. So, it is going to be 7 V naught by 9 R. So, this part is done, this part is done. Now, the energy loss due to friction. So, of course, friction is causing energy loss here till pure rolling starts. So, from the time when the motion starts till the time when pure rolling happens, there is an energy loss. But once pure rolling starts, the energy loss is not there. So, can you imagine that friction is there, but it is not causing any energy loss? That's because friction is not doing work. For energy to be lost, friction has to do work. Why is it not doing any work in pure rolling? Because the point is always at rest. So, work is only going to happen when the force is also going to be associated with displacement. Alright, energy loss. So, all I have to do is, for energy loss, E initial minus E final. So, what is E initial now? Of course, you know, half m V naught square plus half I omega naught square. I has to be mr square by 2 since it's a disk, minus half mv square plus half I omega square. So, you can plug in the values. I'm not solving it. It's just to give you an idea that they can also ask, the question can also ask about the energy loss. Alright. So, I hope you've understood. This is a classic question where you can understand how forward slipping or backward slipping ultimately converts to pure rolling. So, friction would always want pure rolling. Just keep that in mind. I will wait and then we move forward. Alright. So, the next thing is rolling motion on an inclined plane. Very simple. You can imagine you have a circular object, you have a round object, you leave it on an inclined plane, it will start pure rolling. But all that can only happen if the inclined plane is rough. Imagine if it's a smooth inclined plane, it would just skid down without rolling, perfectly smooth. But it's very hard to, in practical life, you cannot have a perfectly smooth surface. So, any round object will ultimately roll a little or more depending on the roughness. But keep in mind, friction would want it to roll, okay, pure rolling. So, let's draw the free body diagram. So, let's assume that the angle is theta. So, let me take this color. Okay. So, this is like mg sine theta. Of course, you know that. Let's assume that the angle is theta. So, this is going to be mg sine theta. Okay. Now, this is going to be mg cos theta. This is going to be the normal contact, of course, and this is going to be the friction. So, I have drawn the free body diagram and I have shown all the 4 forces. So, what is the governing equation? Very quickly. So, the governing equation, of course, is mg sine theta minus friction is equals to ma. Mg sine theta minus friction is equals to ma. Who's rotating this? So, can you imagine when you release it from here, the only and only force that can rotate is friction, because all 3 other forces are passing through the center. So, the only force that's going to provide the torque is going to be friction. So, I would write mg sine theta minus F is equals to ma. Alright. Next, I would write, so this is the equation of F net is equals to ma, just to remind you. Now, similarly, net torque is equals to I alpha. Net torque is equals to I alpha. So, F into R is equals to I alpha. I hope you know the basics. So, F into R is equals to I into alpha, and I write alpha as A by R. Now, you would say why? That's because I am already assuming that it is in the state of pure rolling and this point is not slipping. So, if this point is not slipping, so always 2 conditions will be met. V is equals to R omega and A is equals to R alpha. Alright. So, that's why I am writing alpha as A by R. What do I get? F is equals to I A by R square. Let's put this value in this equation. So, mg sine theta minus IA by R square is equals to MA, is equals to MA. Solving this, you get the value of A. So what are we getting? A is equals to G sin theta upon 1 plus I by mr square. This is giving me the function of acceleration. This is the acceleration with which this round object is going to roll down. Now, as you know, since we can write I is equals to mk square, what can we do? We can write I is equals to mk square, where k is the radius of gyration. This acceleration can also look like this, g sin theta over 1 plus k square by r square. You can also write it like this. So this is giving you the acceleration, and once you have the acceleration, you can also get the value of friction that you're needing here. How? Put it here, this equation. All right, let's call it 1 in equation 1. That's because friction is given as a function of acceleration. So when you plug in this value I by r square into g sin theta over 1 plus I by mr square, all right, this is what I'm doing. So I will get friction is equals to mg sin theta over mr square by I plus 1. This is the value of friction. What friction? The friction that we need. Let's call it the friction required. But we don't know whether this much friction would be available. We'll have to see. Who will decide that? So of course you do know that that's the limiting value of friction. So what is the available friction? So you would say mu n, that is mu mg cos theta. So can we comment that pure rolling is possible only when available friction is more than what is required. Available is more than what is required. So can we write this greater than this? So mu mg cos theta greater than mg sin theta over mr square by I plus 1. Okay, so this gives us mu greater than tan theta over mr square by I plus 1. This is giving me the condition that this much coefficient of friction is needed if you are wanting this to exhibit pure rolling. Otherwise it might roll, but it will roll with slipping, and if it will roll with slipping, then energy loss will definitely be there. But in this case, to your surprise, when it slides down, when it rolls down, we can apply conservation of energy, which should be shocking to you, because every time before we have discussed that whenever friction is involved, you cannot apply conservation of energy, but here you can do that. All right, so I will wait, you copy this down. I have one more aspect to discuss here. All right, so I'm going to pick up the same diagram again and assume, let's say it slides down a height h, okay, and it ultimately reaches here when, let's say, its velocity becomes v and angular velocity becomes omega. So we are wanting to find this v and omega. So what are we going to do? We are going to apply conservation of energy, that is u initial plus k initial is equals to u final plus k final, assuming that it is pure rolling. So we are going to write initial potential energy as mgh, taking this as the reference level, initial kinetic energy as 0 since it was released, final potential energy as 0 because this is the reference, and final kinetic energy is half mv square. Now develop this habit of writing two terms in kinetic energy, translatory plus rotatory. Now in the very next step, I will write omega as v by r. So what am I getting? I am getting the value of v as under root of 2gh over 1 plus I by mr square. Very similar denominator as we had in the case of acceleration. Or you can also write it as v is equals to root 2gh over 1 plus k square by r square. That's the velocity for you when it slides down, and angular velocity is going to be v by r. So a good amount of discussion. In fact, you can do a comparison very quickly here, because you do understand. In fact, I will write it here, that a ring, let me write it with a different color. All right, so let's say, yeah, I of a ring is mr square, while I of a hollow sphere is 2 by 3 mr square. Okay, so the moment of inertia of a ring is mr square, of a hollow sphere is 2 by 3 mr square, that is 0.67 mr square. Of a disk, it is mr square by 2, that is 0.5 mr square. And for a solid sphere, it is 2 by 5 mr square. For a solid sphere, it is 2 by 5 mr square. By the way, a hollow cylinder when rolls down is just like a ring, because if you elongate the ring, it becomes a hollow cylinder. Similarly, a solid cylinder is just like a disc. So if you make the disc thicker, you should rather call it solid cylinder. So if you have a question of hollow cylinder, take it as a ring. If you have a question of solid cylinder, take it as a disc. So I've already written them in descending order. Ring having the highest moment of inertia and solid sphere having the lowest moment of inertia. So now can we comment that ring, the order is ring's moment of inertia is greatest, then is the hollow sphere, then is the disc, and then is the solid sphere. All right, then is the solid sphere. So if this is the order of I, and I is in the denominator of A as well as V, can we say that A of the ring is going to be smallest, then it is going to be hollow sphere, then it is going to be the disc, and then it is going to be the solid sphere. So if for same mass and radius, who's going to roll down with the highest acceleration? The answer is solid sphere. Keep that in mind. So time, since acceleration is less, so time will be more. So the time taken to roll down through the same inclined plane will rather be the opposite order. So maximum for ring and minimum for solid sphere. Now also the velocity. Obviously velocity also has moment of inertia in the denominator. So velocity of the ring is going to be the smallest, and then it is going to be the hollow sphere, then it is going to be the disc, and then it is going to be the solid sphere. So I've given you an elaborate explanation of how things roll down in inclined plane, but keep in mind, if it is only rolling, that is pure rolling, then you can apply conservation of energy. But if it's rolling with slipping, then you cannot apply conservation of energy. Then you will have to apply work energy theorem. All right, I will wait, and then we do one last question, and that will be all about rolling for today. All right, so this is what I wish to talk about. A small object of uniform density rolls up a curved surface. So sometimes it does happen that they have not mentioned which type of rolling it is, so you take it as pure rolling in that case. It reaches up to a height of 3v square by 4g. With respect to the initial position, you have to identify the object. So it reaches up to here, that means its velocity here becomes 0. Can we apply conservation of energy? Of course we can. So u initial plus k initial is equals to u final plus k final. What is u initial? 0. What is u initial? 0. Why? Because we've taken that as reference. We always do that, right? Now k initial is half mv square plus half I omega square, since it is rolling. What is u final? So the answer is mgh. And what is k final? 0, because when it reaches up to the highest point, its linear velocity as well as angular velocity becomes 0. So half mv square plus half I omega we will write as v by r whole square. You of course know that. And the value of h, we will plug in the value that's given in the question. That's 3v square by 4g. So when we solve this, the value of I turns out to be mr square by 2. Would you like to answer? So the answer is a disc, or you can call it as a solid cylinder. So if given in the options, it can be a ring, it can be a disk or a solid cylinder. So this is just the opposite of what we normally do. Normally they would give us the type of object and maybe ask us the height to which it will roll up, but here they have done just the opposite. They have given us the height and instead asking us what kind of an object is that. So we determine the moment of inertia, and through that we can correlate what the type of object is. But that's all for this particular class. It was a very lengthy class, I do understand that, but you know, I was trying to accommodate all the concepts in one class so that you have the momentum. Now you can watch this class again and again just to polish your you know, knowledge of this particular topic. But it's really going to help you a lot, even if you don't have a direct question on rolling. But this is something that has built up a lot of concepts, accommodated a lot of concepts, and it's always not about marks. It's also about, you know, learning how rolling exactly works, because you know, it is something that is very common and you really observe it around you. But that's all. Thank you so much for your time. Happy learning. Bye bye.
If you enjoyed this video, please don't forget to like, share and subscribe to our channel.